All right, folks, so in this video, you want an example problem of a titration problem. I know that you do, because with an example, you'll be able to do extremely well on the upcoming assignment. Trust me, I know these things are going to be super easy. So these types of questions are, again, in reference to something that's called a strong base and a strong acid. And that's really all that we've done so far. It's just been strong base and strong acid. So we've not done anything with weak acids or weak base titrations. Those are completely different types of problems. And the only questions that you're going to see in this very first assignment are strong bases and strong acids titrated together. So there's only a handful of strong acids and a handful of strong bases. There's not that many choices that we can choose from with these types of problems, but the problems are going to be structured in a very similar way. So for instance, you're always going to have a titrant, and let's say for this example problem, the titrant is blah. It doesn't matter what it is, folks. I don't really care what the name of the compound is. And we're just going to assume that it's some type of base. I don't care. And let's say that that concentration is a 0.250 molarity solution. All right. And we are titrating a sample, and the sample has to be the opposite of. So if a base is in the burette, an acid has to be in the sample container down below. So let's say that we're titrating a sample of acid, and the acid is blah. It doesn't really matter what that is either. The names and the structures of these things are not important as of right now. So with the acid, let's just say that we took 10 milliliters of the acid and we pipetted that out into an Erlenmeyer flask, and now we're getting ready to titrate that thing. So during the titration, I've also had to put in some water, typically for a volumizer, and we've put in some indicator just so that I could visually see the color change when this is supposed to happen. And let's say that the color change happens, I don't know, somewhere in the titration. Let's say that we started at a 0.5 milliliter on the burette, and we ended up to be a 12.3 milliliter on the burette. That's when the color change happened. So the question is, what is the strength of the acid? What's the strength of that acid sample? So we're going to use the rules that we talked about in the previous video. And number one, we start with our titrant first most of the time. If this is a typical titration problem where we're trying to find the concentration of the sample, not the concentration of the titrant, but the concentration of the sample, it is the same exact format, the same workup, almost every single time. So the titrant looks like 0.250 molarity solution. So I'm going to take moles and I'm going to divide it by liter, because that is what molarity is all about. And that's the unit that it gave me, molarity, right? So with that molarity problem, I now know how many milliliters it's going to take for the titration. So it's 12.3 minus 0.5. If you can't do that in your calculator, folks, or in your head, do it on your calculator. I don't care. I will never know. Like I've told you before, I don't know. You're doing this online. I'm not going to make fun of you. So 12.3 minus 0.5, and I'm going to hit enter on the calculator, and I get 11.8. Well, that's 11.8 milliliters, and this molarity equation needs liter. So I'm going to divide by 1,000 in order to get liter. If you've got to do that on a calculator, do it. If you can do it by your head, do it by your head. I don't care. So 0.0118. All right, so now this equation, I'm going to erase the liter, and this is going to be a 0.0118. So that is the milliliter that it took for the titration in terms of liter. So now I can solve this molarity problem, right? This will give me the amount of base that was required for the titration. So in order to solve for this molarity problem, well, this is x divided by a number. If I want it to solve for x, I do the opposite of, so that's divided by a number. I'm going to multiply by a number, right? And I multiply both sides of the equation by the same value. So over here to the side, I'm going to take 0.250, and then I'm going to multiply by 0.0118 for the 11.8 mils, and then I'm going to hit equal. So this will give me the number of moles of base that the reaction took, 0.00295. All right, 0.00295. And that's the moles of the base. Whatever the base is, I don't really care. Now, the second part is I have to understand a little bit of the stoichiometry of the question, the reaction that's going forward. So let's assume that this is a 1-to-1 mole ratio. So if this is the number of moles of base, that's also the number of moles of acid that is in the sample, because it's 1-to-1. All right, so I know that. So, this kind of information is going to be provided by a chemical equation. If it's not 1-to-1, then we'll just use the mole ratio and a little bit of stoichiometry in order to fix it. But for this problem, we're going to assume 1-to-1. All right, so now the question is going to say, what is the concentration, right? What's the concentration of the sample in terms of molarity? So I'm almost finished. So how do we get concentration? Well, concentration is typically in terms of molarity, unless it's stated otherwise. And molarity is the number of moles of my sample divided by the number of liters of the sample. This is going to be pretty easy at this moment because I've already solved for the moles of acid. Right up here it is, 0.00295 divided by the liter of the sample that I used. Well, I used 10 milliliters up here in the titration. I need liter though for concentration if I'm doing molarity work. So that 10 milliliter is going to end up being a 0.0100 liter. So that is what I'm going to divide by. I've taken 10 divided by 1,000, and that will give me 0.010. So to calculate the concentration of the sample now, based on the titration values, I'm going to take 0.00295, and I'm going to divide it by 0.0100. I'll hit enter, and the answer that I'm going to get for this problem is 0.295. 0.295 molarity for the concentration of the acid. All right, so that is a typical run-of-the-mill titration problem. Now, what can change? Because we talked about a few of these things that could change in the previous video. Well, one of the things that could change is that maybe instead of molarity, they're giving me normality. So I told you to go back and review those videos on how to convert normality into molarity and vice versa, because that's going to come in handy maybe for some of these, because normality is typically given to you in terms of acid and bases. So I would, once again, in the last video I mentioned it, I'll mention it again. I would, if the problem gives me normality, make sure that you convert it into molarity first using the appropriate conversion factor. Then if the question wants you to get normality as the final answer, find molarity first, just like we did here, and then convert that over into normality in the very last step. If this is a monoprotic acid or monoprotic base, molarity is normality. They are the exact same thing. But if the acid has 2 protons that it can give up, well, my normality is going to be twice as much. If it has 3 protons that it can give up, it's going to be 3 times as much. The same way with the base. If it can have 1 OH group, the normality is the same. If it has 2 OH groups or 3 OH groups, I multiply the molarity by 2 or molarity by 3 in order to get the correct normality value. Because all of that previous information, folks, it's all coming back. I told you that never really goes away. It's just now understood to be out there, and we just understand that you know what to do in these cases like this. But this is your typical titration problem right here, right? You've got a titrant. That titrant took so many number of milliliters, and you've got a concentration of it. So now let's relate that to the sample that you titrated against, and we'll calculate a concentration most of the time for that. All right. So typical titration problem looks just like this. Notice I didn't say hydrochloric acid. I didn't say sodium hydroxide. I didn't say any of those acids and bases. If you notice, I never did anything with the formula weight numbers. It was all concentration and volume based. That is why I did not give you a name, because it really didn't matter. The only thing that does matter is the balanced chemical equation. And very often it's 1-to-1, but it doesn't have to be that every single time. So take a balanced chemical equation, look at the coefficients in front. If it's 1-to-1, great. If it's not 1-to-1, go back and review the stoichiometry videos. Those stoichiometry videos will tell you how to convert one compound into another. So you might have to do that here, right? So for instance, let's say that I've got an equation that looks something like this. NaOH plus H2SO4. Well, if I balance this chemical equation, well, two partners go into a club, or two couples go into a club, and they switch partners. So I'm going to get Na2SO4, and then I'll get H2O. That H and the OH bond up together to make water, and then that sodium and that sulfate bond up together to make sodium sulfate. The problem is that SO4 is a -2. So I need two sodiums to balance that out, because each one of those are a +1, right? Sodium is a +1, sulfate is a -2. So I need two of those in order to balance that compound. Then I go through and I balance the chemical equation. So I see two sodiums here in front. I'll put a 2 there in front, so that's two sodiums as well. Then I see two oxygens from that moment. And then here I just see one oxygen really there. I'll just put a 2 there in front. And then I see two hydrogens there plus another 2. That's a total of 4. 2 times 2 is 4. And then I did not mess with this oxygen and sulfate, because if you notice, this SO4 stays together. That SO4 is one cohort, and that SO4 is still the same cohort. So it's easier if I just keep it together and treat it as one. I've got one SO4 group on the left and one SO4 group on the right-hand side of the arrow. So in this particular case, I get a mole ratio. And that mole ratio looks to me like there's 2 moles of NaOH, and that is equivalent to 1 mole of H2SO4. All right. So that is something that I need to keep in mind when I begin to do the titration math. So when I get the number of moles from maybe the titrant, if NaOH is the titrant, then I'm going to bring in a little bit of stoichiometry here. And this balanced chemical equation tells me, well, moles of NaOH there, moles of NaOH on the bottom. I need to get to moles of H2SO4. So in order to do that, there's a 2 in front of the balanced chemical equation there, and there's a 1 in front of the balanced chemical equation there. So I would take the number of moles of NaOH from the titration. I would divide that by 2, because that's what the balanced chemical equation is telling me to do, and that will give me the moles of H2SO4 maybe in my sample. Then, just like before, I take that number of moles, divide it by the liter in order to get molarity. Once I get molarity, I can then convert that into normality if the question wants me to do that. All right, so this is just one example of how to work out a titration problem. Again, it's pretty much the same process. We're just flipping the acid and the base roles sometimes, or we're starting with a concentration of the sample in order to standardize the titrant and so forth. But it's typically the same thing every single time. Molarity, mole, liter. Molarity, mole, liter. Molarity, mole, liter. That is what the titration problems are all about, at least for strong acid and strong base. All right. So with that said, I think that will give you enough information to start working on these assignments. Keep in mind, the concentration units can be in molarity, it can be in normality, it can be in ppm, it can be in percent concentration, but you treat them all the same. Just keep in mind, what does the concentration unit mean? Molarity is mole per liter. ppm is milligram per liter. Percentage, well, that's gram per gram because it's based on percentage most of the time. Either milligram per milligram, gram per gram, doesn't really matter as long as the units are the same. So I think with this information, you'll be able to answer the majority of the questions. Critically think about them. Just trust yourself and go back and review some of those other concentration, stoichiometry, and normality videos because they might come in handy here with these example problems. All right, so good luck on the assignment. If you need help, you know where I'm at and you know how to get in contact with me. Good luck.